A thermometer looks delicate. A slender glass tube, almost weightless, a tiny bulb at one end, a narrow channel holding a silver or colored thread of liquid, numbers printed along the side. It seems simple, almost minimal. But the thermometer exists at the intersection of physics, perception, and trust. Its current form is the result of centuries of refinement in how humans measure something they cannot see. Temperature is not tangible. You cannot see it directly. You feel it, but feeling is unreliable. What feels warm to one person may feel neutral to another. Early societies judged heat by experience alone, by touch, by observation of boiling or freezing, by the behavior of materials. But touch deceives. Dip one hand in cold water and the other in hot, then place both in lukewarm water. Each hand reports a different sensation. The human body adapts quickly, distorting perception. As science began to formalize in the Renaissance, scholars sought a way to measure heat objectively. Early devices known as thermoscopes appeared in the late 16th and early 17th centuries. These were not true thermometers. They indicated temperature change but did not measure it against a fixed scale. A typical thermoscope consisted of a glass bulb attached to a tube whose open end sat in water. As air inside the bulb warmed, it expanded and pushed water down the tube. As it cooled, water rose. The problem was clear. Air expands not only with temperature, but also with changes in atmospheric pressure. These early devices responded to both heat and weather. There was no reliable separation between the two influences. To measure temperature accurately, the system needed isolation. The breakthrough came with sealing. When a glass tube is sealed and partially filled with liquid, that liquid expands in response to temperature changes in a predictable way. Liquids expand more uniformly than gases and are less sensitive to pressure fluctuations if fully enclosed. The shape of the modern thermometer reflects that discovery. The narrow capillary tube is not aesthetic, it is amplification. When a liquid expands, it increases in volume in all directions. If it were in a wide container, the change would be subtle and difficult to see. But in a very thin tube, the expansion can only move upward. Even a tiny increase in volume becomes a noticeable rise. The aha moment often occurs when you realize that the thermometer is not measuring length. It is converting volume change into linear motion. The bulb at the bottom is critical. It holds most of the liquid. As temperature rises, the liquid in the bulb expands first. Because the capillary tube is so narrow, the expansion is forced upward into the tube. Without the bulb, the system would lack sensitivity. The bulb acts as a reservoir that magnifies the effect of temperature change. Choice of liquid also shaped the form. Early thermometers used alcohol. Alcohol expands significantly with temperature and remains liquid at low temperatures, making it useful for cold environments. But alcohol evaporates easily and can separate from the column. Mercury emerged as a preferred liquid for many thermometers for several reasons. It expands consistently over a wide temperature range. It does not wet glass, meaning it forms a clean, continuous column without sticking to the sides. It remains liquid at room temperature and conducts heat well, allowing faster response. The silver line inside a mercury thermometer became synonymous with precision, but mercury is toxic. Over time, safety concerns led to the decline of mercury thermometers in medical and household settings. Alcohol-based and digital thermometers replaced them, yet the shape persisted. Even digital thermometers mimic the slender probe and elongated body. Why? Because the shape is ergonomic and intuitive. The elongated form allows insertion into confined spaces, under the tongue, into the ear canal, into food. The narrow probe minimizes discomfort while ensuring sufficient contact for accurate measurement. Digital thermometers replaced liquid expansion with electronic sensors, typically thermistors that change electrical resistance with temperature. These sensors convert thermal energy into electrical signals, which are then processed and displayed numerically. Despite this technological shift, the underlying challenge remains identical. How do you translate invisible molecular motion into visible, trusted information? The original glass thermometer did so mechanically. The digital thermometer does so electronically. The scale printed along a glass thermometer reflects another layer of refinement. Temperature is continuous, but scales are discrete. Early thermometers lacked standardization. Different regions used different reference points. Daniel Gabriel Fahrenheit, in the early 18th century, established a scale using fixed reference points, including the freezing point of a saltwater mixture and human body temperature. Anders Celsius later proposed a scale based on the freezing and boiling points of water, inverted in its original form, before settling into the now familiar 0 to 100 degrees. The standardization of scales allowed thermometers to become communication tools. A number on the tube represented shared understanding. Design constraints extended beyond physics into readability. The capillary tube must be thin enough to magnify expansion, but not so thin that surface tension causes breaks in the liquid column. The glass must be strong enough to resist breakage, yet thin enough to allow rapid heat transfer. The spacing of numerical markings must balance precision and legibility. Too dense and users cannot read accurately. Too sparse and small changes are lost. Response time is another constraint. A thermometer must reach equilibrium with its environment to measure accurately. If it responds too slowly, it frustrates users. If it responds too quickly to transient changes, it may give unstable readings. The thin glass wall and small liquid mass optimize response time by minimizing thermal inertia. Then there is trust. A thermometer is not just a measuring device. It informs decisions about health, cooking, weather preparedness, and scientific experimentation. Its reading must be believed. The transparent glass body allows users to see the mechanism at work. You watch the liquid rise. The measurement feels tangible. Digital displays remove visible motion, but offer speed and precision. The trade-off is transparency of mechanism. Many users still instinctively trust the visual column of a traditional thermometer because they can see change happen. The evolution from glass to digital did not eliminate the old form entirely, because both solve slightly different aspects of the trust problem. Even modern infrared thermometers, which measure temperature without contact, maintain elongated shapes and pointed ends. They resemble their predecessors, maintaining familiarity while changing function. Human behavior shapes this continuity. We learn to associate certain shapes with certain purposes. A slender probe suggests measurement. A glass tube suggests precision. Design does not always discard form when function changes. The thermometer also reflects a deeper principle of design. Sensitivity must be controlled. Too sensitive, and the device becomes unstable. Too insensitive, and it becomes useless. The bulb size, tube diameter, and liquid properties are tuned so that typical environmental changes produce readable movement without overshooting. There is an invisible negotiation between expansion rate and visual scale. The moment of realization is this: the thermometer is a translator. It translates molecular agitation, invisible vibration of particles, into visible displacement or digital numbers. The slenderness, the bulb, the scale, none are arbitrary. They are all elements in a translation system. Before thermometers, temperature was qualitative. After thermometers, it became quantitative. That shift reshaped medicine. Fever could be defined numerically rather than descriptively. Cooking could be standardized. Scientific experiments could be replicated precisely. The current form of the thermometer persists because it embodies a resolved solution. It is narrow because amplification requires confinement. It has a bulb because sensitivity requires volume. It has markings because communication requires scale. Even when electronics replaced liquid columns, the ergonomic logic remained. Invisible design often hides in the conversion between worlds. Heat exists at the molecular level. Thermometers make it visible at the human scale. They transform chaos into numbers, and in doing so, they quietly remind us that measurement is an act of translation. A fragile glass tube, a digital probe, a silver line rising inside, all performing the same task, making the invisible measurable. And once you see that, the thermometer no longer feels delicate, it feels precise. A simple shape refined by centuries of effort to answer one quiet question: how warm is it exactly?